Okay, if we have no more questions, we can go on to UAB, which I think is John Costa.
That's me, John Cosamilia, yes. Let's see.
I saw a Roman there.
You saw, okay. So this is an outreach model. So it's mostly for the general public. So the idea is that the master students in the DGQ that are involved themselves in doing outreach, that they can use this material and they can actually maybe also contribute to this. In our group here in Barcelona, we have been devoted to outreach for a while, trying to really convey quantum concepts to the general public. It's about time, no? I mean, they're very important concepts that people really don't know. They know about genome and ADN and whatever, DNA, but quantum is still like magic or something, no? And some things are susceptible for being explained. So we have a bunch of activities involving mostly we come from quantum information, so everything has a kind of this operational and game flavor from quantum information. And I have a bunch of slides. I will just go through them just to have an idea of what kind of things we do. Many of the things are already working. We have tried them and they work. They can be improved maybe and standardized and translated to English, of course. But they include guides for teachers, guides for the students who are following the thing, some Python codes for cryptography or from some other things, and some I will explain now, some materials also, like very simple polarizers and so on. So one important part is cryptography, and here there's a part on classical, so nothing to do with quantum. But of course, quantum key distribution is a solution for that, so it's nice. And we start with a substitution code and explaining what they are, a bit of modular arithmetic, and then they have a guide to understand substitution code, transposition. Then they have to try to hack and to convey this idea of the eternal battle between hackers and encoders, and how the decoding depends on the context, the kind of public key distributions that rely on one-way functions and so on. So there's a Python packages to do frequency attack, very simple. It's very, but it's also simple to use. I mean, this is oriented to high school students. Then the public key distribution, we have some games to encode these ideas of some mathematical functions that are easy to compute in one way, but not reverse them, and they can try it out. Then the one-time path is illustrated by these overheads in a way that you have a message and a key, and when you put them together in the one-time path, the message emerges, and the same for another message. For example, that you have a poof H bar, and the one-time path is called one-time path because if you try to use it twice, and you mix the two encoded things, you get information about both, right? So this is very visual. And they like it a lot. And of course, you can create an image that you like for your own public, no? Then we use, we do quantum key distribution also, and we do it in a way, in a very with the light of a cell phone and polarizers. There's two teams, Alice and Bob's, which were classes in a way with polarizers either in one basis or the other one. And then if they close one eye, they detect zeros or ones, and the sending also with polarizers, and they implement the very basic BB84 protocol, okay? And they see what happens if there's a spy or not, and they detect it. So it works quite well. Also for Bell inequalities, we have a game, okay? So we phrase a Bell inequality like in a very simple game that you show some cards and they have to agree on some strategy to win money. And then they write their strategy and they play the game, and they realize immediately that at most they win on average 2. Okay, and this is very, you run that. I mean, if you have a big group, you run the thing many times, and you can do statistics. And they go to the IBM quantum computer, and they see that the probability of winning is much higher. No, these impossible things that quantum suddenly it becomes possible. Then we have another model on metrology, that we try to just convey the idea of what is estimation, why precision increases when you repeat the experiment many times, and then finally, also in the IBM quantum computer, very simple, like GHZ methodology. So these are the three major teams we have, and the idea is to, I don't know in what form. I mean, also we have ICFO in the same node in Barcelona, which are also very active in the GQ. So maybe we do something together, or we use it in networks. We don't know exactly in what form this will go, but I just want to put this forward so that showing that we're available and happy to discuss ideas and share ideas with all of you. Thanks.
Thank you so much, John. That was fantastic. Do we have, so I have a question for you as well. You talked about the outreach part of it being used by maybe the GQ students who are already doing outreach. Do you see maybe, my comment, or at least would be, or my first thought would be that the networks would be a good place for this. Is that what you have in mind as well?
Yeah, I don't know, actually. I still don't know how the networks are forming. I was a bit surprised on this kind of random division. I think it was more or less random, no? It's interesting. It's an interesting experiment. I would have more try to put the groups together with common trends. I don't know, quantum information, many-body, quantum matter, or outreach, or something like this. But let's see how it works. I don't know. Maybe we can have contents which appear in several networks depending on the topic. But that's part of these things that I really don't know how we will actually implement it. It's a question that I put forward to. If there's any ideas, we have the materials more or less ready. It would take some effort to put them maybe in a nicer form and to make them that they work better and more efficiently. We're not professional in that, so